Right, guys, how you doing? So I'm Lee Kennedy, and I'm the senior chemist at Gtechniq. What I want to talk to you guys today about was kind of the science and the chemistry behind ceramic coatings, a little bit about how they work, what the differences is between different types, and how we can identify that, and what we're doing to then try and push the industry forward and make improvements. So let's start off with what is a ceramic? So it's a term that gets used a lot. We normally think of it as like sort of pottery and tiles, these type of things. So from a chemist point of view, a ceramic is an inorganic, non-metallic substance. So when I'm saying that, what I mean is by inorganic, I mean that's not based on carbon chemistry. So carbon has a unique property that it can just bond to itself endlessly and therefore make huge complex molecules. So we are made out of carbon-based molecules, all biology, that type of thing, but all the way down to wood and various polymers and plastics is all carbon-based. So a ceramic can't be based on that. Non-metallic, fairly obvious, isn't made out of metal. So how does that apply to our coatings? How does that actually work with them? So these are polymeric coatings. So normally when we talk about polymers, we're talking about plastics. But again, that's carbon-based chemistry. So with ceramic coatings, this is based on silicone with an E on the end. So we're talking about polysiloxanes and polysiloxanes. What they are is they're very long chain molecules, which would be repeat units. So polymer, poly meaning many, mer meaning a unit. So for a siloxane, that's a silicon and oxygen, just repeat, repeat, repeat. And then for a siloxane, it'd be silicon and nitrogen. So these very long chains have little side groups coming off them. These little side groups can link together to give you a kind of ladder structure that they can then build into a three-dimensional cage structure. This is a process called cross-linking. The most common type of cross-linking is vulcanization in rubber. So again, this is something that's used in lots of industries and something you will have come across before. Polysiloxanes cross-link through moisture curing. They can react with the moisture in the air, which then catalyzes a reaction. It can be through heat, through thermal curing, and through reaction with UV. So some of the properties you'll get from a silicone or ceramic coating are hydrophobicity, so water repellence, chemical resistance, thermal and UV resistance. They can be heated up very high. They don't yellow, they don't crack under UV absorption. They're very mechanically resistant, so they're resistant to abrasion, and they're also electrical insulators. So how does that all tie in with paint protection? So ceramic coatings were first developed for the electronics industry, and they're using what is known as conformal coatings for silica chips and circuit boards. And they're mainly there as protective coatings. And the majority of the production and the manufacture of ceramic coatings has been for the electronics industry. But around 25 years ago or so, people started recognizing that they had the exact same properties that was needed for paint protection, mainly in the automotive industry. So again, water beading, dirt repellence, cleanability, abrasion resistance, and increased slickness. So when we talk about those qualities, and like I say, I know a lot of you guys in here are detailers, so you've all seen it. How do we know one coating's better than the other? How do we actually measure it? And the thing, so I said this has been around 25 years. That's still quite a novel industry. This is still new technology. So the world of standardized testing, so be that ISO or ASTM, etc., hasn't really had the chance to catch up with this yet. So there are no actual international standard tests to gauge how good a ceramic coating is and the duress that it goes under in its lifetime, be that on a car, a boat, a bike, etc. So one thing me and my team have been working on over the last 5 years is to build our own standardized testing protocol. And that ties in with the 25 years of anecdotal experience that Gtechniq have in the business, plus the feedback that I get from our accredited network, which is quite widespread and has a lot of knowledge and is always there to help feedback to me. So we know how well our coatings perform. So now in the lab, we're trying to standardize that so we can actually get repeatable results. So I'll take you through a few of the methods that we use. So we have a contamination resistance method. So obviously you apply ceramic coating, you want to keep your car clean. So how we gauge this is we've developed a standardized synthetic road grime, which is a mixture of clay and oil and salt and all the other type of contaminants you're going to pick up as the vehicle gets driven around. Spray this onto the surface, and when I say the surface, it's a test panel about so big that we've got a body shop down the road who will paint those out for us with a standardized automotive paint. So we know it's the same hardness of top coat, the same every single time. We'll then apply whatever ceramic coating we're testing to the surface and apply this contamination spray onto it. We leave it to dwell, we pressure wash it off, take a series of measurements I'll take you through in a moment. Then we put it onto what's called a scrub machine, which is a standardized bit of kit with a sponge that goes backwards and forwards and with a standardized wash solution. So the point of that is if I wash a car, if you wash a car, we're going to apply different pressure. You might apply different pressures on different days. You might be slightly quicker. This will always do exactly the same. So we're controlling the variables. The measurements we take, so our contact angle measurements. So obviously we measure water, which is what the car is going to be exposed to. But water is a very small polar molecule. So its bonding characteristics are driven by the slight positive, slight negative in the molecule. A lot of dirt and grease is made up of large non-polar molecules. So we use a substance called diodymethane, which is a sort of synthetic oil. And we take the contact angle measurements of that as well. Now, and from that, we can calculate something called surface free energy. So surface free energy, simply put, it's the non-stick frying pan effect. It's how hard it is for anything to adhere to the structure. So, and the reason why we get water beading is because of this. So a bead of water wants to pull itself into a sphere because of its surface tension. When it contacts the surface is trying to pull it and make it spread and wet out. The less energy on the surface, the less it can make it wet out and the tighter that bead becomes. So we can measure this, we measure it very accurately using a bit of kit called a tensiometer. And then as we do this, we just keep repeating these contamination, clean and measurement cycles. And what we're trying to do is recreate car getting driven, car getting dirty, and a car getting washed. That way we're actually seeing how the coating can behave in the real world. And we've got a really good correlation between how we know our own coatings behave and the results we're getting. So this enables my lab to be able to test things in a couple of weeks that we need 60 to 100 cars being driven on different roads because no two cars get dirty the same, and you need 2 years worth of testing and checking data to come back. So it's meant we can make adaptations to new formulations and improve products much quicker and with much greater accuracy. The next one we'll be looking at is abrasion resistance. So what we're talking about here is the very light swirling and marring you get during a wash process. So one of the standard tests that's out there is things like pencil hardness, but that doesn't really accurately represent what the coating is trying to do. It's too deep and it's too aggressive, and more often than not, you're measuring the hardness of the surface underneath the coating rather than the coating itself. The coating is only around a micron thickness. To put that in perspective, a human hair is 70 microns. So we have developed a test using a standardized abrasive felt, and we've tried many different materials to do this to get the right results. We've actually locked in on this one. When I say standardized, I mean that is made to a very tight criteria, and we buy it in and it's always exactly the same. So again, this is the repeatability and reproducibility. We know that we're testing the performance of the coating, not of the variables that could come into it. If we use different types of felt, it can make one look very good, one look very bad, when in fact they're about the same. So we're trying to keep everything the same, so the only variable is the performance of the coating. And again, this is done by a machine, so it's a set speed, set weight. And then we're able to compare that to standard, just to normal uncoated paint. So if you look at the top image there, that is a coated surface where it's only got those few scratch marks in it. And then the bottom image is just standard paint as it would come from the factory. Now these are microscope images, so you're very unlikely to make your car look that, or you'd have to do a very bad job of washing it. But this is giving us a really good gauge of how well it actually increases the performance. And we're able to see with quite good accuracy the differences between different coating systems. Finally, we test something called coefficient of friction, which is the slickness of the surface. So to test this, we have again, it's a machine test, so we have a little die with a weight on it that gets pulled across the surface, and it measures how much force the drag of the surface creates. So that is giving us, again, a quantifiable measure. Again, slickness is one of those things that's quite subjective by hand. You can, obviously, when you apply a coating, the surface becomes much slicker, but how slicker is it? Have we made improvements, and how repeatable that is? And one of the things of slickness is it's going to give a better roll-off angle. So you can get very good hydrophobicity, very good water beading, but if that bead doesn't shed at a very slight angle, that can stay behind and leave watermarks behind, etc. So you want a low coefficient of friction to give you a good roll-off angle. Now, with those three tests as well, they work synergistically. And what I mean by that is that if you have a car that's cleaner and stays cleaner, and therefore you'll have a more efficient pre-wash at the initial stage. So any aggregate particles are going to be removed before you do your contact wash. You've also got a harder surface and a slicker surface. So it's harder to mar a slicker surface because there's less friction for any aggregate particles, and the surface is harder and more mar resistant anyway. But it's also much less likely because you've made the surface easier to clean and you remove those particles. So we have a decent understanding of the technology. We have an improving understanding of how to test it and how we can measure what makes a good ceramic coating. But what does make a good ceramic coating? So first thing is, not all ceramics are created equal. So I've talked in the past about traditional quartz coatings and composite coatings. So composite coatings is a term we've used to refer to Gtechniq's more advanced coating systems because of the way they layer themselves. But what I'm really talking about here is the original coatings that were developed for the electronics industry that do a good job at paint protection, and coatings that have been taken from that and developed specifically for paint protection. And some of the ways we do this is I was talking about these side groups, these side chains, these little branches off the long main chain of the polysiloxane molecule. So we can adapt their reactivity. So the simplest example of the polysiloxane is PDMS, which you all know that's the sealant we get in bathrooms and in kitchens. So that is a very simple molecule with a very small unreactive side chain. But by giving different groups, so this could be various things like epoxies or amino functional groups, we can harness the reactivity of how these lock together, how quickly they react, and then how strongly they react to give us a different coating altogether. Also, there'll be different additives within the solvent system, so adhesion promoters, and also people underestimate how important the solvents are as well, because the solvent isn't just there to hold everything together. It's not a cheap thinner. They are actually designed as well to slightly soften the paint. So basically open it up so the coating can key into it, chemically bond and become the top layer. So what I'd like to concentrate on now is a bit specifically on the chemistry of the polysiloxanes and on the silica as well. So SiO₂ content. So this is a term that again gets brought up quite a lot, and I think there's actually quite a bit of confusion in the industry between SiO₂ and the silicones, the polysiloxanes, because they are quite similar in certain ways, and I'll discuss why that's important. So SiO₂ is a very small, so it's one silicon and two oxygens. It's a very small molecule. It's actually hydrophilic, so it attracts water. And we know this because you get silica desiccant pouches in food, etc. So when it's ground up, it has a very high surface area. It can actually extract moisture from the air. But it is very hard, so it is glass. So to scratch a piece of glass compared to, say, a bit of wood or a bit of plastic is very difficult because it is a hard scratch-resistant substance. Polysiloxanes, as I've mentioned already, are very long molecules. They are flexible until they start cross-linking. So depending on how well you cross-link them will depend on their flexibility. And they're incredibly hydrophobic as well, so very repellent to water. So that's an incredibly simplistic diagram of what it would look like, with the red circles being silicon molecules or atoms, and the little blue ones being oxygens. So the top line is the chain, and then you have these side branches forming this kind of ladder structure. And these gaps here are quite important because that is where the silica nanoparticles end up. So when we talk about nanocoatings, we're referring to the use of silica nanoparticles. So a nanoparticle is any particle that has its maximum dimension is less than 100 nanometers, which is incredibly small. So we impart silica into the polysiloxane formulations to give hardness and scratch resistance. And this is a process called grafting. And there's three different mechanisms we can do this by. The first one is by hydrogen bonding. So hydrogen bonding is when in water where you have a positive and a negative, with the positive part being the hydrogen. We can use this with the silica and with the polysiloxanes to actually make them attach. Now this isn't a permanent chemical bond, it's an electrostatic attraction. But this is why when you have a bottle of ceramic coating, you don't have a load of little bits of sand at the bottom, because that's what it would look like if it wasn't for this. The polysiloxane change, which will dissolve into the carrier solvents, hydrogen bond with the silica and entrap it. There's also covalent bonding, so we can actually permanently chemically bond some of the silica nanoparticles to these reactive side chains. And I'll discuss the different techniques and why we wouldn't do this as well. And finally, most importantly for the cured coating, is network entanglement. And that's when those ladder structures, the gaps between the chains and the side branches, actually fill up with silica particles. The silica particles as well will have some sort of surface treatment to them. That will enhance the hydrogen bonding, and it will dictate the chemical bonding as well. So we can actually treat them at a very, very low film thickness level with various, again, using different sort of silicon technologies. The reason this is important is one of the reasons why silica, in my opinion, is the best substance to impart hardness into a ceramic coating, is because it's a very similar chemistry. You have the polysiloxanes chains and you have the SiO₂ molecules. So it's all silica technology. So there's a simpatico between the molecules. They want to bond together, they fit together physically. Whereas using other technologies, graphene would be a good example. If you see a graphene coating, it'll all settle out on the bottom because it won't graft in the same way that silica will. You will get the network entanglement, but you won't get the other advantages, and your ability to tailor the coating are therefore reduced. So that's a lot about molecules. What does that actually mean? So this is a scanning electron microscope image that some of you, if you've ever listened to me ever do anything before, you will have seen before, because we're very proud of these images. A standard optical microscope that you look through magnifies things about 1,000 times. This is a 2 million times magnification. On the left, we have the quartz, the traditional, the old school electronics type coating. And then we have a more modern composite coating designed for the paint protection industry. So you can see here, it's about this thickness compared to a much denser, thinner layer. And in here we have these very large dark gaps, which are holes, they're pores within it. At this level, this is open. Now, even at such a tiny level, that can fill with dirt and grease and contamination, which is going to make the surface look dull, less glossy, and it's also going to help attract more dirt. So the denser composite structure is much more repellent to this. And this is why we're seeing the improvements in performance for an automotive or marine-based coating. So everything I spoke about at this point, the different techniques, the different ways of bonding, leads to this. So that's an actual picture of what's going on. But this is what's given us the improvements in performance. So that is good performance, and that is excellent performance. And that's the difference between something that's designed for one purpose, but kind of works, and something that's been specifically designed for the purpose of paint protection. So following on from that a little bit, I'd just like to discuss why a two-coating system is needed. So, as I was saying, silica is there for hardness, but it's also hydrophilic. So the harder you make a coating, the more scratch resistant you make the coating, the more likely you are to reduce its hydrophobicity, its water beading, and you're going to reduce its dirt repellence as well. So for optimum results, what you'd be looking at is a base coat that has a very high level of this network entanglement. And one of the things we do with our coatings is we have a very specific size range of silica nanoparticles as well. This is very closely controlled. So we have some larger and some smaller. The larger ones sit, and then the smaller ones sit in the gaps to fill a very dense layer. And this is what's going to give you optimum scratch resistance within a coating. But as you'll know, anyone who's used coatings like CSL, CSU, they start off with good hydrophobicity, but that dies off quite quickly. That's because this enhanced, you'll get some layers of the silicons that will be removed, and then you have this dense structure underneath. That's why we always advise using the top coat, which has lesser of the silica in it, and it's a more polysiloxane dominant coating. So that top coat is going to give you your dirt repellence and cleanability. Your base coat is going to give you your scratch and your scratch resistance and hardness. Now, there is one way to get the best of both of those worlds, where you can get very, very good cleanability and reasonable hardness, but that would be sacrificing durability. So the way this is done is to look at different ways of grafting. So different grafting techniques, different surface preparation for the silica nanoparticles will mean that we can actually come up with a one-coat system that will give you the best of both those worlds. But because a lot of the side groups will be taken up during the grafting process, we can't bond the coating together as strongly. So it's going to physically break down. And therefore, you can't get the same length of durability you would do with the two-coating system. So following from that, I just want to run you through some of the new products that are coming out. And relevant to what I've just said is GT1. So GT1 is a very entry-level beginner ceramic coating with 1 year durability. And we've managed to design this with some things I've spoken about today. So the surface treatment of the silica nanoparticles, the grafting techniques, and the way we've balanced that, we've managed to get excellent cleanability and water beading with a good level of scratch resistance. But the payoff for that is that it's only going to last for about a year. But because of the nature of the coating, we're quite happy with that level of durability. If you look at our product range, we have C2, and then we kind of jump to CSL. And there's a big step there. So this kind of sits somewhere in the middle, and it'd be something that the first-time user, maybe someone who's used waxes in the past, but maybe is a little scared to try a ceramic coating, well, to use with confidence. We've made it very, very easy to apply. And some of that ties in with the properties I've spoken about today, the different ways that you graft the silicon nanoparticles, the reactivity of the side chains. So if you take something like CSU, CSU is our most durable coating, lasts for about 9 years. The reason for that is because it's so reactive. It reacts so quickly, but that means it reacts very strongly and really locks in and gives you this incredibly durable coating. The payoff for that is it's our most difficult to apply. That's why it's accredited only. So some of the new ones moving away from the coatings, we've got a new snow foam coming out. So this is, it's going to be a sugar surfactant-based product. So most traditional detergents are based on petrochemicals or byproducts thereof. But a lot of new technology is coming out using basically plant-based technologies to create cleaning products. We've been looking around that and we've built this new system, formulated a new product. So with it, we have absolutely superb detergency. So it really pulls the dirt off much better than its predecessor. And it's got excellent foaming characteristics as well. But again, this is tying into, it's part of our R&D strategy to make Gtechniq products more sustainable. We are ISO 14001 accredited, which is the international environmental management standard. So we're always looking for sustainability, but we've also got the outlook that sustainability can't be a compromise because compromise isn't sustainable. We need to be improving performance with this as well. We're not going to move back and say, okay, this is a much more environmentally friendly product without the performance. And we believe we've got it there with the new snow foam. Fabric proof. So this is a textile treatment. Mainly for our bike market, but we could be looking to all sort of outdoor and performance wear. So this will, it will give, first of all, it's a DWR, durable water repellent. So it will make any garment water repellent. We even tested it on uncoated cotton, which is the hardest thing to make waterproof, and we're still getting reasonable results with that. On top of that, it contains an antimicrobial additive, so it stops the buildup of odors, which can, eventually ruin performance sportswear. And also it's abrasion resistant. Now we looked at this two ways, because at first I wanted to see and benchmark against the competition in high wear areas, so particularly shoulders, if you have a rucksack, the seated area for trousers, etc. If you're a cyclist, how much does that affect the performance of the treatment? And we found we're excellent. But then we looked at it a second way, and it's a technique called a martindale, which essentially is an abrasion technique. It's something that's been done for years in the textiles market. And it sees how abrasion resistant a bit of fabric is. And we actually found that by treating a bit of fabric with this, you increase the abrasion resistance. So if you have an expensive jacket or any performance sportswear, it's actually going to prolong the life of it for quite a significant while, whilst delivering excellent waterproofing performance. We have a rinseless wash, which you guys this side of the pond are probably far more accustomed to than we are in Europe, but I think we will get caught on. What we've done here is we found maybe some of the rinseless washes out there which offer a little bit of protection, etc., are trying to do too many things. So we're focused purely on a cleaning product. From a more technical point of view, we work with the University of Warwick in the UK. And they have a material science division called WMG, which is one of the world leading sort of surface analysis departments. So they're the people who do our scanning electron microscopes for us, because a scanning electron microscope costs about £3 million. So apparently I'm not allowed to buy one for my lab just yet, but they'll happily work with us. And the person who operates it needs a PhD because it's a very complicated bit of kit. And to actually understand how to get the images and actually get the resolution is very difficult. But we work with them. They're absolutely superb departments we're working with, really good people. So we're getting some more scanning electron microscope images, more focused towards the marine market. So we're looking at GRP. GRP, again, at these sort of levels is incredibly porous. It's, it's full of holes. It's like a crumpet almost. So we want some images of some uncoated GRP, and then showing the difference the coating makes physically to this surface and how that can actually prevent the build of dirt and help preserve the surface. And finally, we've been working with QLab in Arizona. doing some accelerated weathering tests. Again, this will be largely focused towards the marine market, where we're looking at how ceramic coatings prevent UV degradation. Now, this is something that anecdotally we've had a lot of feedback on. And now we've actually got some certified third-party proof that it is the case. We're about halfway through the test, and the data is definitely showing that having a ceramic coating on the surface is going to stop UV damage. One thing from my point of view is I don't actually know why. Polysiloxanes, ceramics themselves are incredibly UV resistant because they're transparent to UV. It passes straight through them. So we don't understand why it can prevent the surface underneath getting damaged. So that's something that I need to research, look into, some papers and get my head around, maybe speak to some people who know more than I do. So we can get an understanding of, so again, it's the same process of, we know from years in the market how something works. We get some standardized, qualifiable tests that actually show us, yes, this is the case and this is by how much. And then we need to understand why, so then we can keep pushing things forward, improving our products, and hopefully helping the whole industry and you guys as well. Okay, that's everything from me. So thank you very much for listening to me talk about molecules for a long time, and hope it was worthwhile. Any questions?
What was the name of the oil that you used as a standard for the contacting?
Diiodamethane. So diiodamethane. So it's two iodine molecules on a carbon.
Can we go back to the spot where it said optimum performance? That was the right.
So what bit was that?
Can you go to the spot where it was talking about the two-coat system, higher levels of silica,
Okay, so
optimum performance? I was writing it down.
yeah. So the more silica you add into the system and the more densely packed that silica is, the harder and more scratch resistant the coating will be. But you're going to start losing hydrophobics. So the water beading is going to get worse and worse. Yeah. So you'd want a base layer that's densely packed with the silica. And then you have a top coat that has much less silica in it and is more dominated by the polysiloxanes, which are very hydrophobic.
Okay.
Does that clear up?
Yes, thank you.
Right at the back.
What's the difference between a automotive coating and a marine coating?
About $10. No, sorry, forgive me, I'm facetious. Our marine coatings are the ones that we have seen the best or UV resistance in. And they are some of the older technologies as well. So we've maintained them in the marine line simply because the feedback we already has is that, and also have a very unstandardized test on the side of the building at Gtechniq headquarters, where we basically applied some coatings, and the ones that maintained its color best and had the less fading were the marine coatings. So there are some slight differences. Again, it's just to do with nuances of the chemistry, but in principle, they're exactly the same.
So does that mean there's more UV protection in the marine coating?
There's nothing we actually put in there to give UV protection. It's an inherent property of the coating itself. Now, as I was saying, it's something that I don't fully understand yet. It does it, we know it does it, and now we've got proof it does it. But I need to understand how and why, so therefore we can start making improvements and making it even better.
Do you see the benefit of multiple layers of the base coat and then put a top coat on top of it?
No. As long as it's been applied properly, as in working in small sections, making sure you get full coverage, chances are it's like to start rejecting itself anyway. So building it up, you're not going to really see much improvement in performance at all. It's just going to take more of your time, more money, more product. I mean, from our point of view, you use twice as much of our product. But no, I don't think there's I've never seen anything that suggests to me there's a big improvement between 1 and 2 coats of the same system.
Elaborating on that a little bit, can you talk about the difference between being able to layer a quartz-based coating versus not being able to really layer a composite-based or Gtechniq-based coating like that? And then second part of that would be, going back to what you were saying about a layerable system or a two-part system, if we know we're not going to layer crystal serum ultra, then with regard to Gtechniq coatings, that second layer, are we talking EXO, are we talking C2, and maybe talk a little bit about how that two-part system works?
Yeah. So quartz systems can still be layered. Composites can be layered. You're just not going to get a great deal of benefit of building up. Because it's only just the surface that matters. And like I say, they're incredibly thin. So it's not like when you paint a wall where you have to do 2 coats to get the coverage, and because you get the see-through. You're not actually adding much more to it. So it's only best to layer if you're adding a second layer which has different properties to the first. And certainly, so for automotive, we'd suggest either CSU or CSL as a base coat. So CSL is just an adaptation of CSU. It's less reactive and it has slightly less silica in it. And then EXO is the top coat because that's there for your hydrophobicity and your cleanability.
I just wanted to continue a little bit more with you said that our base layer is more dense with the silica.
Yes.
And that's what makes it more durable, more scratch resistant.
More durable. Sorry, more scratch resistant. So
hydrophobicity, correct?
yeah.
Okay, and then, so when we put a top coat on it, what is the predominant ingredient in the top coat?
So it would still have some silicon nanoparticles in there, but it's not going to have anywhere near as many as the base coat. So it's the polysiloxane chains will have the more dominant characteristic, and they are very hydrophobic, very dirt repellent.
Thank you.
Okay.
With Gtechniq Marine, you have the base coat and then you have the top coat.
Yep.
I've done a few boats with it now. Why is it gets very gooey, the top coat, and it just gets very staticky, like it shocks you like really bad. I mean, what's causing that?
So the static is from the electrical insulation, which is one of the inherent properties of a ceramic, of a polysiloxane. So it's just the buildup of charge within it. And it's probably coming more from the boats, because if it's a GRP boat, you've got, it's a whole insulator. So if charge builds up in that, it's going to build up in a point, and then you touch it, it goes through you. The coating could well be making that worse. The gooiness, yes, that is, again, just the way the coating's formulated. If I was going to be working on a new marine top coat tomorrow, I'd certainly look at something that's better to apply. There's the short answer there. So it's just kind of, yeah, it's kind of quite it is quite a thick coating. That's just the nature of it, yeah.
Can you use it on cars?
Can do, yeah. Yeah, all the marine coatings work on a car. All the car coatings work on a boat. They're just more specific for what's best there.
Extra would you get for putting it on a car?
I wouldn't suggest using it on a car. I'd go for just CSL and EXO, yeah.
Just curiosity.
Yeah, so the similar properties, it's just to do with the marine environment and the UV especially, that the base and top has shown us that gives the best UV resistance. So cars aren't getting the same level of UV degradation in car paint isn't as sensitive as GRP is. So it's not as a required function. So we're sticking to the auto for that. Okay. Yes.
Is there an ideal dyne level for the performance that you had on slide 4? And I was just curious, what what is the actual catalyst for the process? Is it heat, is it the pressure of the leveling,
Yeah.
air?
So, did you say dine level, as in dine pens? So a dine pen will measure down to about 30 millinewtons per meter. We're getting down to about 16. So very low. So that is surface-free energy. That's how it's measured. So a dine pen is an example of surface-free energy, where that basically it can't wet out anymore because you reduced the surface down. A dine pen has very different substances in there, so it'll have polar and non-polar parts, and that's what you're looking at there. So yeah, with our coatings, we would certainly, you'd always want to be under 20. So if you can wet out with any dime pen, which is at 30, that's not a very good coating. Uncoated paint is about 40 off the bat. The reason I say 20, and it's just a fairly arbitrary number, but that is what you would class as omniphobic, which is both resistant to water and to oil. So that's giving you real repellency. So as soon as you start going to that 20 mark, you have got a surface that is going to stay very clean. And sorry, there's a second part to your question, wasn't there?
What is the catalyst to get the cross-linking in the product?
The catalyst is moisture in the air. Yeah, so we use moisture curing catalyst. So that is why it'll be in a solvent. So the solvent is water-free, and we also purge the there's no actual. Doesn't require that sort of catalyst. They're so reactive by themselves that when they start getting exposed to air, they'll just start cross-linking and reacting. That's why they can start curing in the bottle if you leave the caps off, or in the PET, for example, as well, because they get exposed to the moisture. We purge all the bottles with nitrogen, so that's completely dry. So that's to get any of the moisture out of the air in there to stop any reactions starting before you start applying them. But that is why when you get it on the surface, you'll see it start beading out, because that's it starting to react in as well. So it's quite a chemically reactive substance, and that so it doesn't need a catalyst to be added into it for the reaction to occur. It just happens by itself by reacting with itself and the moisture in the air. Yes, sir.
I had a question, kind of an opposite of everything that's going on. It's the greatest project in the world. I love it. Back in the 80s, I used to be the Teflon guy and detail and babysit people. But now I've done PDR and wheel repair for about 28 years. It's a problem. Glue pulling, it will not stick to the car. Great product, but when you have to spend somebody's money and deal with the insurance company, I've been told, how the heck do you get this stuff off? It's so badass, so.
Yeah.
I won't touch it. I've heard that you have to literally compound it down. Now, that being said, you don't know you're working on a wheel. The guy just spent $1,000 on having all this, his Bentley wheels done until your paint goes crap, Can't really get in there and compound everything. So what's your suggestion? I know it's the opposite of what we're talking about here, but remove any ideas that can help our business.
Sadly not. You are going to have to compound it. Yeah, because I've just talked about all the positives of our coating, and that is until it comes to getting them off, because they're designed to be durable. They're designed to stay on there, and they're also designed to stop things sticking to them. So that doesn't help you out at all, does it? That you can get very small, like inch size polishers, that type of thing. If you look directly behind you, that young gentleman there is far more versed in this subject than I am. So directly behind you there, waving his hand at you. Yeah, that's Carson. So he's our, yeah. So he should be able to give you some better advice on physically how to do it. Yeah, he does all the actual real work in the detailing bay on cars. I just talk about molecules. But yeah, but sadly, the coating's designed to make your life very difficult. So yeah. Yes, up there back.
So, at my shop, we have multiple coating manufacturers we use.
Yep.
What exactly makes a coating easier to use per se? Because I have one coating I've used where I could slather down the whole car pretty much and then level it all off in one go. And then another coating, I could apply it and I won't have any more longer than a minute to level it off. What's the difference between those two?
So the difference is going to be down to how reactive the side chains are. So the more reactive they are, the quicker they react and the better durability you'll get. And certainly with our range, can't speak to any other products, but we always tailor it that the easier it is to apply, the less long it's going to last. If you can do a whole car in 5 minutes, you don't mind if you have to do it again in a month. If it's very difficult to do and very complex and involved, so getting towards CSU, for example, where you can only work in very small areas, you have to control your environment, you have to be aware of the humidity factors, that lasts for 9 years. So generally, if something's hard to apply, it's got to last, because you don't want to be doing it every year or every 6 months. So that's generally, in my opinion, the differences between it. So something where you could go around a whole car and then come back and buff off probably won't last that long, because that slows, it's got very slow curing, which shows the chemical bonds aren't going to be as strong. So therefore, physically, it will break down through mechanical abrasion, washing, etc., and getting dirty. Okay? Yep.
For your Crystal Serum Ultra, it's 9-year coating. Is that 9 years without any sort of top coat or anything?
No. So you won't get 9 years of hydrophobic performance from it. You'll get 9 years of scratch resistance. So if you want both, you want the best of both worlds, you would have to reapply the top coat within its lifetime. So EXO is 2 years. So you need to apply EXO 2 years over that 9 year underneath. But it just means that when you come around to replacing the top coat, you do a 1-stage polish, do your top coat, and you're done. You don't have to keep going through reapplying CSU. Now CSU is going to be there, but again, you can just top it up. It's a bit like if you put C2 on top. So that's going to be gone within 3 months or whatever, but the CSU is still going to be underneath. So EXO's not as durable, not scratch resistance, but it does give you the hydrophobics and cleanability. When that starts to dart off, you can give it the 1-stage polish, reapply.
Does the 9 years, does that kind of go with the UV resistance too, or does that kind of fall under the EXO?
No, but the 2-coat system will give you the best of the UV resistance. Yep.
So with regard to the 9 years, obviously, it's not going to last 9 years in every situation. I think as detailers, a lot of the times, we get asked by customers, leads, whatever the call them is, how long does a coating last? And usually what I'll tell them is, well, how do you drive the car? How's the car live?
Yeah. Is it a daily driver? Does it sit in a garage? Are you washing it with a brick? You know.
You coat 2 cars. One of them is a garage queen, and then the other one sits outside. And 20,000 miles a year. So, what would your response be to someone who's asking how long it's going to last, and maybe to that end, what would the degradation be on a vehicle that does sit outside 24/7, 365, gets driven 20 to 25,000 miles a year? What is that 9 year?
So,
if there is any real data.
Well, we give a 9-year guarantee, and we get a complaint on 1 in every 10,000 installations about it not working, and that's normally about the hydrophobic performance, not the scratch resistance. It's a difficult question. It's how long is a bit of string, because no 2 cars are the same. On 1 car in my last 20 years.
4 years, 4.5?
I'm fairly confident of that 9 years. Really? Yeah, even on a daily driver. It is that good. As long as it's looked after within a reasonable standard. You know, like, so if someone's going through, sort of all-made car washes or that type of thing, using really caustic TFR, maybe that's going to bite into it. But yeah, the main thing is the guarantee. So they're not happy with performance, they can claim on it, but people don't. Again, like I say, we know from the durability and everything, lab testing, but actually correlate directly to a number of years, there's just too much variability to it. So,
What's the difference between GT1 and EXO?
So GT1, it's got like less durability than EXO. Its actual initial hydrophobic performance is better though, but that dies off quite quickly. And that is all to do, like say, the grafting of the silicone nanoparticles and the way we've sort of arranged the molecule to form a coating. So we've managed to get really good cleanability, hydrophobics, reasonable level of scratch resistance for a one-layer system, but we've paid for that through the durability. But it's only meant to last 1 year anyway. It's probably a little bit easier to apply than EXO is as well. You can work on quite big areas if you're confident to. We'd probably advise for the first time user, work on half a panel at a time, just so they can get a feel for it. But yeah, it's again, they're all similar chemistry, but it's just been adapted to be a more user-friendly version.
One more question. Snow foam compared to G-wash, what's the difference?
So snow foam is a pre-wash. So the idea with a pre-wash is you're getting as much of the dirt off the car or the boat or whatever it is before you physically touch it. Because if you just go straight in on a filthy car and start hand washing it, you're just going to scratch the living daylights out of it. So pre-wash chemicals, be that something like an all-purpose degreaser or a snow foam, are designed to be pulling that dirt off without you physically touching the car. So you try to get the car as clean as it can be before you actually start doing the manual wash. Yep.
Do you think the new one coming out, G1, can we use that as a top coat and sell it as a yearly maintenance instead of doing twice?
Yeah, we'll work on top of all the other base coats as well. We haven't marketed it that way, but for you guys that are installing professionally, if that's something you wanted to offer your customers, yeah, you could do. It would work on top of one of our base coats. Instead of doing EXO every 2 years, you could do this as a yearly one, drum up a bit more business for yourselves. Any more? Yep.
When you reapply a coating, say after 4 years, you're just like a decon and then you just reapply?
You would normally advise maybe doing a one stage, depending on the condition of the car. You can just do a decon and reapply. From a chemical point of view, there's no issue with that. But maybe just giving it a very light polish, just to lift the car up a bit, take out any of the scratches that may have gotten into it over those 4 years, and then you can reapply. But it's not necessary. You just need to get it clean and it will bond to it. Okay, I'm going to call that. Thank you for listening, guys. Really appreciate it. Hope you enjoyed it.